You ever see this happen? A brilliant idea in science, one that seems so promising, and then it just, poof, vanishes. On paper, it's perfect. But when researchers actually go to test it, the effects they're looking for is just gone. It happens all the time, and it leaves us with this huge puzzle. All right, so let's really get into it. The big question we're tackling is exactly that. Why do so many solid, well-founded ideas seem to just fall flat when they get put to the test? It's not always because the theory itself is wrong. Nope. The answer is usually way more subtle, and it's hiding right inside the study itself. So to figure this out, we're going to treat this whole thing like a scientific whodunit, right? We've got a crime, a scientific effect that has mysteriously disappeared. And lucky for us, our lead detectives, researchers Aguiniz and Stone Romero, have given us all the forensic tools we need to investigate the crime scene and start rounding up the culprits. Okay, so in every good detective story, there's always a key person of interest, right? In our case, that's something called a moderator variable. Now, this isn't the smoking gun, but it's a factor that can completely change the story. Think of it like a dimmer switch for a light. You're studying the link between flipping the switch, that's variable A, and the light coming on, that's variable B. The moderator, that's the dimmer knob. It changes the strength of that relationship. Is the light off? Is it dim? Or is it blazingly bright? The moderator is what decides. So what does this actually look like out in the wild? Well, imagine a company using a test to hire new employees. The whole point is to see if a high test score predicts you'll be good at your job, right? But here's where a moderator, like gender, can reveal something huge. The test might be fantastic at predicting performance for men, but totally useless for women. See, if you don't look for that moderator, you could just say, yep, the test works, when in reality, it's deeply biased. That's why finding these things is so important. But, and this is a huge but, there's a catch. Finding these moderator variables is ridiculously hard. I mean, way back in 1971, the psychologist Sheldon Zedeck called them elusive. And you know what? That name has totally stuck. Researchers know they're out there lurking in the data, but they're just masters of disguise. And this leads scientists to give up on what could be perfectly good theories. So the real question is, why are they so hard to spot? All right, time to continue the investigation. If the moderator is our elusive person of interest, well, it turns out they have accomplices that are helping them hide. In science, we call these methodological artifacts, but you can just think of them as the usual suspects who are known for sabotaging studies and making real effects completely vanish. Drawing on the work of Aguiniz and Stone Romero, we've got a lineup of 5 prime suspects. Now, each of these is notorious for draining a study of its statistical power, and all that really means is its ability to find an effect that's actually there. So who's in the lineup? We've got small sample sizes, unequal subgroups, range restriction, predictor interpolation, and a small effect size to begin with. Let's pull a couple of these into the interrogation room. First up, let's talk about suspect number 2, unequal subgroups. This is a classic. It happens all the time when you want to compare 2 groups, maybe men and women, but your study has like way more of one than the other. And this chart just shows you the problem perfectly. When you've got a nice, even 50-50 split, your study has high power. But look at that other scenario, a 90-10 split. The power just takes a nosedive. Why? Because it's incredibly hard to tell if what you're seeing in that tiny 10% group is a real effect or just, a random fluke. You just don't have enough data to be sure. Next on our most wanted list is a real sneaky one, range restriction. This is what happens when the data you're looking at isn't the whole story. It's like trying to judge an entire movie by only watching the final scene. This table is the perfect example from the world of hiring. On the left, you see the test scores from everybody who applied for the job, a whole range of scores, from low to high. But the company only hires the people who got the top scores. That's the group on the right. So later, if you do a study to see if the test actually works, you're only looking at the all-stars. You've restricted the range. By throwing out all the data from the low and average scores, you've made it almost impossible to see the real connection between the test and job performance. The effect is hiding in plain sight because you've tossed out most of the evidence. Okay, so we've got our suspects, but how do we prove they're the ones killing these studies? I mean, you can't just go back in time and rerun thousands of real-world experiments. This is where the researchers got really smart. They conducted a massive digital forensic analysis. It's a method called a Monte Carlo simulation. Basically, you can think of it like this. They built a digital world on a computer where they knew for a fact that an effect was real. Then they ran this virtual experiment thousands and thousands of times. Each time, they'd introduce one of our suspects, like a small sample size or an unbalanced group, and they could precisely measure just how much damage each one did. It's like a scientific crash test. And what they found in the simulation? It was pretty shocking. This wasn't a case of one thing going wrong here or there. No. What the simulation uncovered was something that looked a lot more like a coordinated attack on the truth, a conspiracy. Yeah, the big reveal here is that it's rarely just one lone villain. That's not how it works. In the messy reality of scientific research, these problems, they hunt in packs. The real danger wasn't one single suspect, but the way they conspire together.
So let's look at the evidence. First, we establish a baseline. Under absolutely perfect conditions, we're talking a big sample size of 300 people, no other issues, the study's power to find a real effect is nearly perfect, almost 100%. As you can see, it's a slam dunk. The study finds the truth, no problem.
But now, watch this. We keep that exact same big sample size, 300 people, which sounds great, right? But this time, we just introduce one of our other suspects, severe range restriction. And bam, look what happens. The study's power plummets from almost 100% all the way down to about 60%. That means there's now a 40% chance the study will just completely miss an effect that's really there. The two factors are working together against the researcher. This table right here, this is the full confession. This is the forensic report. In the top left, perfect conditions, you get perfect power. But look at the bottom right. We still have that big sample size, but now we've got both unequal groups and severe range restriction. The statistical power just collapses to a pathetic 26%. And this is the absolute key takeaway. The damage isn't just 1 + 1, it's multiplicative. These suspects work together to make a real, meaningful effect practically invisible. So, after all this investigation, what's the verdict? What does all this mean for us, the people who read the headlines and try to make sense of the world based on scientific studies? Well, it really comes down to this incredible line, often credited to the great Carl Sagan: the absence of evidence is not the evidence of absence. Just because a study comes back and says, we found nothing, doesn't mean there's nothing there. It could just mean the study itself was a victim of this conspiracy of problems, that it was a low-power study, basically designed to fail before it even started. And this matters a lot. It means that brilliant, game-changing theories might get tossed in the trash by mistake. It means that biased hiring tests or even ineffective policies could get a green light because the studies designed to check them just weren't strong enough to find the flaws. But the good news is, this makes us smarter. The next time you see a headline saying scientists find no link between X and Y, you can be the detective. You can ask the right questions. Hey, how big was the sample size? Were the groups they were comparing actually equal? Could the data have been restricted somehow? You get to be the one who looks for the clues. And that really leaves us with one final, kind of mind-blowing question to chew on. If so many studies out there are underpowered, just think, how many incredible truths, how many important discoveries are still hiding out there in plain sight, just waiting for a study that's powerful enough to finally find them?